So today let's talk about periodic trends, not so much the direction of periodic trends, but really how we can understand why periodic trends work the way they do and how we can write good answers that get us good points on the AP exam. So really the fundamental point with all of our periodic table trends is the relationship between atomic structure and Coulomb's law. And this is Coulomb's law. This is the mathematical expression of Coulombic attraction plus minus charge attraction. And it's not so much that I'm worried about you understanding or writing down the equation, because nobody is going to ask you to do math and solve for the magnitude of the force. It's really the relationships in Coulomb's law that's what we're looking at. And that should be something that we have from our Coulomb sim on Monday, that when we look at Coulombic attraction, the force between the charges is directly proportional to the magnitude of the charge and inversely proportional to the square of the distance. So let's look at that in a little more depth. So what we know is that the charge got bigger as the number of charges went up. As we increased the amount of charge, the attraction between the nucleus and the electrons is going to get larger and larger and larger. We also know that the electrostatic attraction gets much, much bigger as the electron distance to the nucleus got smaller. And that is a squared relationship. So if I double the distance to the nucleus, the attraction to my electron is now only a fourth of what it was before, because remember, it's 1 over the distance squared. So if the distance goes up by a factor of 2, the force goes down by a factor of 4. It's 1/4 of what it was. So electrostatic or Coulombic attraction is a very strong force, but the fact that the force is proportional to the inverse square of the radius means that its effective range is very, very small. So it's a strong force, but it only works over small distances because of the way the force-distance relationship goes. So we have a graph that we made from Monday that looks like this. The attraction force went up linearly as our nuclear charge went up. And the attraction force is directly related to the ionization energy. We'll talk more about that in a minute. So you can see this graph as the ionization energy increases. The attraction force goes up faster than linearly as we get closer and closer to the nucleus. It's an inverse square reaction. So we had a graph that was clearly non-linear here. And really fundamentally the thing is, vocabulary is king. This is a place where wording is going to be really, really critical. This actually comes up more than once on the AP exam, that just stating a trend is not a justification. I like to say that atoms can't read. They don't know where they are on the periodic table. So saying that fluorine is smaller than lithium because fluorine is further to the right of the periodic table, that's not really a why. It's not like fluorine looked at the periodic table and said, oh, better get over here. That's not how it works. So justification of a periodic trend or atomic property is really going to hinge on using Coulombic attraction and Coulomb's law. And that means that there's really two ways to argue. We're either going to argue about charge, an increase in nuclear charge most of the time, or we're going to be arguing about the distance to specific orbitals in the atom, oftentimes the valence shell, the farthest out. Not always, but oftentimes. So let's look at our first trend, ionization energy. And we know the way the arrow should go. We learned that in first year. So we expect that ionization energy should increase as we go across a period to the right. And it does. Lithium is only 520, fluorine is 1521. Ionization energy, remember, is removing 1 electron from each atom in a mole of atoms. So 1 electron going from lithium to lithium plus, going from fluorine to fluorine plus. 3 times the protons means 3 times the force. We expect the ionization energy to decrease as we go down a group, a vertical column. And that's because if I look at a vertical column, say if I go from fluorine to chlorine to bromine to iodine, I go from putting electrons in the 2p to the 3p to the 4p to the 5p, and the distance to the valence shell gets bigger and bigger and bigger and bigger because each time I go up a principal orbital level, the orbitals get larger, and the force is going to fall up as the distance goes up. The force will go down. So I want you to think about this for a minute. If an electron has a stronger Coulombic attraction to the nucleus, does it take more energy to remove or less energy to remove? More attraction is going to require more force to remove. The metaphor I like to use is we all have that one friend who's dating that guy that you're just like, oh my God, how can you not see that he's totally not even in your league, right? And when they first get together, she's just, oh, he's so great. And they spend all their time together because they're just really strongly attracted to each other. And so even when he does his creep stuff that he does because he's a creep, she's so attracted to him that they don't break up. They have a strong attraction, so it's going to take him doing something really, really lousy to get her to break up. So what you really need to have happen is for it to get to be Christmas break or summer vacation where she's not going to see this guy every single day. Maybe it's going to be 3 or 4 weeks until she sees him again because he's on it's summer and he's being a creep and he's not paying attention to her. So now she's got some distance on this guy. And some of the attraction is starting to wear off because we got some distance here. We can kind of see, you're right, he is kind of a creep. So as there's less attraction, it takes less for her to see that maybe they really should break up. So stronger the Coulombic attraction, the more force it's going to take to break that attraction. So here are the arrows for ionization energy. As we get smaller and smaller atoms, because the electrons are in closer and closer valence shells, the ionization energy increases because a smaller distance means a much greater force of attraction and a much greater force required to remove. As I go across a period, I get larger and larger and larger nuclear charge on the same orbitals. So a greater and greater and greater charge means greater and greater and greater attractive force, which means harder and harder and harder to remove, a greater and greater ionization energy. So let's take the trend for atomic radius. We have a very similar idea here. We're actually using the same arguments. We expect atomic size to shrink as the force gets bigger and bigger and bigger. So if I think as I go across a period, the nuclear charge is getting larger and larger and larger and larger. Each time we go to a different element, we add another proton and another electron to pull on each other. More and more charge means more and more attractive force and more tiny atoms. Then if I think about going down a group, remember I said I'm putting those valence electrons in the 2 subshell, in the 3 subshell, in the 4 subshell. We get more and more distance from the nucleus. The greater the distance from the nucleus, the less attractive force, and the atom is getting bigger and bigger and bigger. So here's the directions for the arrows here. As I go towards the left, the atomic radius increases. As I go down, the atomic radius increases. Less charge, less attractive force, bigger atom. Greater distance, less attractive force, bigger atom. So a third trend is electronegativity. This is one of the big 3 trends. Electronegativity is a concept that's designed to think about shared electrons in a covalent bond. And Dr. Linus Pauling came up with a way of basically quantifying this, but the numbers are really just a scale. It's just setting this number as the biggest and then we're taking fractions of that. So fluorine is the most electronegative element. It shares the least evenly. It's kind of the playground bully of the periodic table. Let's share your lunch money. And everything after that is arranged downwards. It's really not critical that you memorize these specific numbers. It's that you need to know the trend in the numbers, because different textbooks will define fluorine as 3.98 or 4. So they're not going to ask questions about specific electronegativity values without providing you those electronegativity values in the question. AP is not going to ask a question that you could get wrong just because you have one textbook over another textbook. They're all approved textbooks. Well, how do I make a Coulombic attraction argument about electronegativity when it's talking about shared covalent bonded electrons? Well, we kind of assume that the more Coulombic attraction I have towards my valence electrons, towards my own electrons, the more attraction I also have for shared electrons. Another way, like I said, I like to use a lot of metaphors. So the metaphor I use for electronegativity is it's that person in your friend group who has the good house. You know, they have the PS5, their parents buy the good snacks, they let you go up in the upstairs rec room and they don't bug you all the time. The good house. That's where everybody hangs out. You hang out at the good house. If on the other end, you've got an atom that's less electronegative, that's like, for my poor kids, my house. My house was not the good house, because if you had to go to my house, you might have to be polite to your chemistry teacher on a weekend. Ew. So my kids would go hang out at their friend's house so that they didn't have to deal with me. So here's the trend, here's the arrows. It is the same as the ionization energy trend. Is the more attraction I have for my own electrons, the more attraction I have for shared electrons also. So a couple of other smaller trends. Electron affinity. Electron affinity is one that is associated with, it's basically the opposite of ionization energy. It's associated with adding one electron to the atom in the gas phase. And this one is a little bit interesting because the trend down a group is very clear. In all of these cases, as I go down a group, I would have to add electrons to farther out shells, and that means that they have less and less attraction. A greater distance has less attraction. So it's less energy released to add an electron there, or needed to add electrons there. So as I go down, the magnitude of my number gets smaller and smaller and smaller. Across a period, you really can't do a great prediction. It can increase, it can decrease. We can say that numbers that we expect to gain, elements that we expect to gain electrons, usually have a larger magnitude of electron affinity. The other thing that's annoying about it is that some things will report electron affinity as negative, some will report them as positive. So you really want to look at the magnitude of the number and look for changes in sign. Like, I go from here where I expect carbon to kind of not really form an ion, it really forms covalent bonds, to nitrogen, which does form a negative ion, and the sign kind of changes. So my other trend that I like to mention is the trends in lattice energy. And lattice energy is actually a little bit different because it's not an individual atomic trend, it's a ionic compound trend. The other thing I will notice in very large capital letters is that lattice energy is not about dissolving. It is oftentimes similar, but you cannot make a dissolving argument from lattice energy data because the process is very different. In lattice energy, we are separating these into gaseous ions. And dissolving, there's a whole other set of interactions that we have to deal with between the solvent and the solute. So they're oftentimes similar, but you can't use lattice energies to decide whether something is going to be soluble or not. So if I look at this chart, I want to think, why is the lattice energy of lithium fluoride so much greater than that of cesium iodide? Can I use the same sorts of arguments about Coulombic attraction? Well, I really have, remember, two parts of Coulombic attraction. It's either distance or charge. And in this case, I really can't make a charge argument because both of these are 1 plus and 1 minus. So the charges are not different between cesium iodide and lithium fluoride. I can't explain something being different by pointing at something that's the same. So if I can't argue about the charges because the charges are the same, then maybe I can think about it in terms of distance. Lithium and fluorine are very small atoms that make small ions. Cesium and iodide are large atoms that make large ions. So think about, if I'm trying to make a crystal, it's like I'm trying to pack them into a box because crystals are nice and solids are nice and organized. So if I try to pack ping pong balls into a box, those ping pong balls can nestle really closely to each other, and I can put lots of ping pong atoms in the box. So small ions like lithium and fluorine, they can get really close to each other and have really strong attractions. A large bunch of atoms like cesium and iodine, it's like I'm trying to fit softballs into the box. They can't get as close together, and as the distance goes up, the Coulombic attraction goes down. So it's even still the same kind of argument here. So I have 3 little examples here, and then we'll practice this more on Tuesday. So here are some questions. Within a family such as the alkali metals, so this is a group, this is group 1A, the ionic radius increases as the atomic number increases. Now, one thing you really do want to pay attention to is how is this question worded? Notice it is asking you specifically to use principles of atomic structure. So if you say something like, well, atoms get bigger as we go down a group on the periodic table, that's just stating a trend. That doesn't get you points. What we have to think about is something about the protons or the electrons or the orbitals, something about atomic structure. Well, again, if I think about the alkaline metals and I think about where am I putting their valence electrons, the valence electrons for lithium are 2s1. Then in sodium, it's 3s1. Then in potassium, it's 4s1. So the argument I would want to make here is a claim evidence reasoning argument. So let's make a claim. The ionic radius increases as the atomic number increases. Okay, well, let's think about why. Well, the radius increases because the electrons are in larger orbital shells. They're in the 2 shell, they're in the 3 shell, they're in the 4 shell. So a larger shell means that those electrons are farther from the nucleus. Now I've used atomic structure, the actual structure of the orbitals, to explain my claim. So I like B. There's actually really 2 ways I can argue about B, and we'll actually look at the other way to argue about it when we look at things on Tuesday. But again, I've got to think about a charge versus distance argument. I know that the distance to the chloride ion radius, it is bigger. It says so. So I can't argue with the test. If the test tells me a piece of information, I need to use that piece of information. So I know that the radius is going to be bigger. So now I have to think about why that might be. And so my argument is actually still a Coulombic attraction argument because it's still an electrostatic question. But what I like to look at is what is the difference between chlorine minus and chlorine? And the difference is that Cl minus has 1 more electron. So if I have 1 more electron, I have more negative charge. And if I have more negative charges, then actually I do have more force, but I have more repulsive force because all electrons repel each other because of their like charges. So I have more repulsive force, and that pushes my ion out and makes the ion bigger. So it's even still just a Coulombic attraction argument. More electrons in this subshell have greater electron-electron repulsion, and that makes the ion bigger. The last one here is about magnesium, and it talks about the difference between the first, second, and third ionization energy. And this again is another one that we'll hit on Tuesday more, but if I look at the first, second, and third ionization energy, I have to remember that the ionization energy is something that I'm taking one electron off at a time. So the first ionization energy is going to give me Mg1+. The second ionization energy is taking Mg1+ and making it Mg2+, taking off another electron. The third ionization energy would be going from Mg2+ to Mg3+. See how that works? And I would maybe suggest that when you think about this one, write out the electron configuration for magnesium. Because as you see it, it's 1s2, 2s2, 2p6, 3s2. So those first two electrons are coming from the 3s orbital. The third electron would have to come from the 2p6. So what's the fundamental difference between 3s and 2p? Well, it's distance, right? 3s is farther from the nucleus than 2p. So when I get to the 2p subshell, I have to overcome greater Coulombic attraction because the distance to the nucleus is smaller. And as the distance goes down, the force of attraction goes up. A really common thing to do is for people to try and just make an argument, well, you're disrupting a noble gas configuration. Oh, okay, yeah, but remember, that's not really arguing from atomic structure. And what's really important about the noble gas configuration, I mean, it's one of those, you have to look at something that's different to argue about a difference. I don't think it's as strong of an argument. I think you could make an argument, but I think you're going to need a lot more data than what you have. Because again, you don't just want to state a trend. You don't want to just say, well, noble gases are lower energy. Okay, great. Why? So it's a much easier argument to just look at the simple argument in the distance here, rather than having to make more complex quantum mechanic arguments about the lower energy, slightly lower energy of full subshells versus unfull. Like, how about use a big difference to explain a big difference? All right, well, we will practice this more on Tuesday. We'll have more practice on writing these claim evidence reasoning arguments, because that's really what the challenge is in AP. Y'all know the directions. It's figuring out how to relate that to the attraction in the ion and write how that's going to work out. And that's why we're going to practice it